Okay, we can get started with the second part then. My name is Andrew Yates. I'll be covering fairness and ranking part two, as you know. And this part, we're going to talk about learning to rank and some more advanced methods. So we'll begin with offline learning to rank. We'll go into more detail shortly, but this is learning to rank where we learn a ranking model with data that was collected offline. After setting up this background, we'll transition into online learning to rank, where we essentially refine a ranking model based on people interacting with the system. And then after a short break, we'll switch topics to fairness in these two contexts of learning to rank with offline data, and then fairness and online learning to rank, where we're learning a system as users interact with it. So let's begin with offline learning to rank. So the task of automatically constructing a ranking model is offline learning to rank. This is using training data so the model can sort new objects according to their degrees of relevance, preference, or importance. So this is essentially ranking a set of items, learning a model to rank a set of items. To make this a little more formal, we have a ranking function f. And what that ranking function does is it predicts relevant scores in order to order documents. This is, of course, making some assumptions. The one assumption here is that we can take each document as input, or we can look at each document as input separately and come up with a score that characterizes where we should place that document in the ranking. If we think ahead a bit to fairness and how this interacts with other considerations, obviously one score is probably not enough. This score characterizes the utility of this document, or the predicted utility, how highly it should be ranked, but it tells us nothing else about how that document relates to other documents. In a very traditional offline learning to rank context, you can think of even ambiguous queries. For example, you have a query like apple. Maybe apple is the fruit, maybe apple is a type of computer. You probably, or a search system probably wants to balance these two senses in order to satisfy the user, so that if the user is searching for the computer, their document could be found in the top items. If the user is searching for the fruit, their document could also be found in the top items. Of course, when we move to fairness, these considerations become more important because now we're not just talking about satisfying the user's preferences, but the items themselves also need to be treated with some care. But that's foreshadowing a little bit. So what we're talking about now is a ranking function f that predicts relevant scores in order to order documents. So here we have an example. We have three documents, document 1, document 2, and document 3. Here, the score of document 2 is greater than the score of document 3, which is then greater than the score of document 1, the score predicted by that function f. And so we have a ranking D2, D3, D1, according to that offline learning to rank model. Now these documents are represented as query document pairs. We create a feature vector for each query document pair. There are different types of signals that go into a feature vector. So essentially, the idea behind this, before I go into specific signals, is that we want to characterize how relevant a document might be to a given query. So for example, we want to know how many of the terms in the document are in the query, or actually vice versa, how many of the query terms appear in the document. And we also want to know other things about that document. Is it, for example, the concatenation of all of Wikipedia? If so, then there could be many terms in it no matter what, but it's not necessarily a good result to return. So this is something like a document length feature, perhaps. When we compare the query and document, we want to think about relevance and how likely it is that those terms would have simply appeared by chance. So we often use some sort of relevance score rather than pure overlap. So now I'm talking about matching signals, which you can see on the left. Overlap would simply be looking at the number of terms that appear in both query and document, whereas a relevance score is calculated using some sort of ranking heuristic. So for example, TF-IDF is a straightforward, very well-known ranking method. TF stands for term frequency. This is how many times a term appears in a document. You can think of this as a proxy for term importance. If a document says Apple many times, it probably is more about Apple than if it says Apple once, but this is only a proxy, of course. The other half of TF-IDF is inverse document frequency. That's the IDF. And so this is basically a measure of how often the term occurs across a corpus of documents. So if you think of a term like the, this would occur essentially in every document or in most documents in an English language corpus. So even though the might occur in the query, our score shouldn't increase very much when we see the in the document. It doesn't tell us much about how well they match because the just appears everywhere. To put things in a little more of a human intuitive way, we're not really that happy if we see the in the document given the in the query. We know that seeing the is not that meaningful. So this is the basic idea between for that first relevance ranking method, TF-IDF, that you see on the left. BM25 is a very effective, empirically more complicated version of this, essentially. I'm not going to go into the formula or any exact details, but basically BM25 is considering document length in addition to simply the frequency of terms and their IDFs. And in addition to document length, BM25 is also has some notion of what I would call term saturation. This simply means that if you've seen Apple, I don't know, 50 times in a document, you're not that happy when you see Apple the 51st time. It's very clear that this document is about whatever type of Apple we're talking about, and the document shouldn't benefit a lot from having, say, 51 versus 50 matches. To put that a little bit more formally, going from 0 to 1 occurrences of that term should have a much bigger increase in the score than going from, say, to 50 to 51. This specific intuition isn't so important for this lecture. I just want to give you an idea of how these matching signals are created. One other matching signal I'll talk about briefly is query likelihood. And this is not that different from TF-IDF intuitively, but this is formalizing something as formalizing the scores as probabilities. So we can ask, what is the probability of this query term appearing in the document, for example. Now, these are all different types of matching signals that indicate what kinds of terms occur in both query and document, and how much and how the occurrence of these terms indicates relevance. We also have many other types of signals that could be included in order to help this learning to rank model that we're training. For example, we could look at document popularity. So is this a domain like Wikipedia that is considered to be somewhat trustworthy and appears often on the web? One way to measure this is how many pages link to the document or linking to Wikipedia. This is much more common than, say, a personal website. Another type of signal could be a document spam score. So we might have some sort of machine learning model or other classifier that takes that document as input and predicts, whether or not the document is spam. If we're thinking, moving more into a ranking humans sort of context, we might think of, for example, the years of experience on a CV, although there might be some reason to be careful with this. We could think about signals related to the query as well, not only to the document. So we could, for example, consider the length of the query. Long query is simply more likely to match terms, more terms in a document. Whether or not that matters depends on the other signals we have. In web search, a common signal on the query side could be something like whether HTTP or www is present in the query. The reason for this is people very often search for websites. So rather than typing a website like google.com directly into the search bar, they might actually search for it. Or with a modern web browser, you might think you're typing something into the search bar directly and then end up searching for that web page because it redirects what you type to a search engine. And so checking for a feature like a string like HTTP or www in the query can help the learning to rank model basically handle that document more accurately. Because, for example, if www is in the query, maybe rather than using all of those matching signals normally, we want to use a very specific matching signal that's comparing the query to the URL of the document specifically. So we can short circuit the normal process, for example. Again, the specifics of all of these are not extremely important for today's presentation. I just want to give you an intuition for why these exist and how they might be used. The models we're going to talk about today are typically not implemented as decision trees, but you can think of the handling of many of these signals in that sort of way. So the way I talked about this HTTP or www string matching feature is really something suited to a decision tree, where perhaps we check to see if that string is in the query, and then there's a different branch of the tree we go down to produce the final score, as opposed to a situation where we don't have that string in the query, and we go down a different branch of the tree, and maybe here, we're weighting BM25 and TF-IDF and so on in a very different way. Another thing I hinted at is that with this string matching feature, I said that we're comparing the query to a URL directly. So if you're coming from an industrial background, you might already be thinking of different document fields. But a document, is usually not just one monolithic object. There's usually often different sections to a document. So if we think about CVs, there's different sections to a CV. If we think of a web page, there's a URL, there's often a title field, almost always. There's a body field with the document content. And so we might be computing these matching signals between the query and between different document fields. So for example, part of the way a learning to rank model like this could help is it could learn, the right way to weight a TF-IDF score between a query in the title of a web page and a TF-IDF score in the body of a web page, for example. Thinking about CV, maybe it learns to highlight some sort of more recent experience more than older experience or something like that. But we can treat the fields differently. And so these feature vectors often contain many different signals. The general way to produce these would be to add in all of the signals that we think might be useful, rather than trying to carefully choose a few. I obviously can't talk about or don't even know about very specific, in industrial systems, but thinking about academic benchmarks and how people often develop these models, you might expect over 100 different types of signals being included. Maybe many different variations of matching signals for each type of matching signal, that matching signal against all fields in the document, and maybe all the other signals you can think of. And these other signals you can really break down into query signals, things like query length, or things that are computed based on only the query, and document signals, like the document popularity, document spam score, years of experience, et cetera, that I mentioned earlier. So to sum up this slide, the main thing to take away is that these feature vectors are representing query document pairs. So we have one vector for every pair that's characterizing the relationship between the query and the document. And these feature vectors are composed of many different types of signals, both matching signals and signals specific to the query only or to the document only. So this brings us to our first question. You can go ahead and join WooClap with the code above, FINDHR 8. I'll give a few minutes for people to join. And the question I'll go ahead and read. When choosing features, so these types of signals to use with the learning to rank model, matching features are useful to have, but they are not essential. So this is true or false. So I'll give everyone a few minutes to think about this and enter their answer, and then we'll discuss it afterwards. Seems like most answers are in. I'll give you another 30 seconds or so in case anyone wants to put in a last minute answer. And then we'll take a look. All right, last chance. Let's see what we got. It's about 50-50%. 46% of people true, 54% false. So this is a pretty good split. Um, I'm happy to talk through the explanation, but before I jump right into it, I wonder if anyone is interested in outlining their thinking in either direction or asking a question to clarify. So this is it's intentionally a little of a tricky question. So we did talk about two types of features on the past slide. We talked about these matching features, and we talked about other signals that are based on either the query only or the document only. And so because we talked about two types of features, I think one could easily have the impression that both of them are interchangeable. That's not entirely true though. And the key part of this is that with other signals, we're only looking at the query or we're only looking at the document. So we're never able to say the query and the document match with an other signal. We can only provide information to improve the ranking. So it's actually the matching signals that allow us to personalize, so to speak, the ranking for the query. It's these matching signals that look at the terms in the query or the content of the query and look at the content of the document and decide how well they actually match. With the other signals, things like spam score, document popularity, years of experience, and so on, navigational strings in the query like www. With these other signals, they help us rank the query better, but they don't actually tell us how well the query and document match overall. We might know that this document is probably not spam. We might know that the document is a really popular website like Wikipedia from that spam score and that popularity score. And we might know this query, you know, has a term in it like HTTP. We might know the query is fairly short, but this doesn't really tell us whether this specific Wikipedia page is relevant to this specific query. We need to know, the query said Apple and this Wikipedia page said Apple, or the query said Mac and this Wikipedia page talked about, different types of Apple, but it didn't use the word Mac. It might have used Macintosh, but not Mac because it was about a different topic. So we need that matching signal in order to understand that the content actually matches between these two. So I'll go ahead and move on. Please feel free to ask if you have a question as I slowly move to the next slide. So the way we represent a query document pair is always pointwise. If you haven't seen that term before, it's not important. Basically, it means that our feature vector is always based on a pair. So we always have one query and one document. And the reason I say it's pointwise in quotes is because when we talk about a loss type, so an objective function used to train the model, we have three different types, and one of them is pointwise, where we look at only a query and document in isolation. Now, the reason we have different losses is because this is typically a model trained with stochastic gradient descent or some sort of optimizer used with neural models these days, like Adam, AdaNet, stochastic gradient descent, and so on. Sorry, AdaGrad. And so a loss function is used to calculate the gradient and perform some weight updates in order to understand how our model should change in order to perform better or worse. So a pointwise loss function looks at only this query document feature vector, one single vector, and says if this vector is labeled relevant, we want to increase the score we get from that vector. If the the pair is labeled as not relevant, so irrelevant, might be that Wikipedia page Apple and the query searching for Apple. Non-relevant might be, I don't know, a Wikipedia page on Amsterdam and a query searching for Apple. For the non-relevant pair, we want to bring the score down. And for the relevant pair, we want to bring that score up. The point is we're only looking at one single feature vector, one pair. Now, a pairwise loss means we look at multiple feature vectors, specifically two at once. With listwise, we'll look at more than two. So with the pairwise feature vector, what we're saying is the score of the relevant pair or the relevant document, which is represented as a query document pair, should be greater than the score of the non-relevant document, which is again, represented as a query document pair. Some examples of this are a hinge loss or maximum margin loss or a rank net, which we'll look at shortly. The third type of loss is a listwise loss. And so this is essentially saying the score of relevant documents should be higher than the score of non-relevant documents. So rather than looking at one single feature vector or one pair of feature vectors, we're looking at multiple feature vectors. An example of this is lambda rank. And the reason we might care about this is because ultimately what we're producing is a ranking. We're not giving the user, typically with a ranking task, one single document, but we're producing a ranking of different documents. And so we might want to be able to optimize that ranking more directly rather than hoping things work out as we would like them to when we optimize individual scores of documents. And I'll show an example of how the two are not necessarily the same. So RankNet, I mentioned on the last slide, this is a popular pairwise loss function. And this is taking two documents, the representation of a relevant document and the representation of a non-relevant document. This could be a little tricky, but I want to reiterate that when I say the representation of a relevant document, this is a feature vector constructed based on the query and that document text and other features, about the query in the document, as we talked about a few slides back. Same thing for a non-relevant document. We represent the document as this feature vector that's considering the query, that document, definitely matching features, talking about how well the query matches that document, and then also other types of signals indicating things that would be useful in ranking the document, but don't get at that key question of how well the query and document matched. So we have that there on the left side of the formula. We're looking at a relevant document, DI, and a non-relevant document, DJ. On the right side, essentially what we're looking at is the difference in the scores the model assigns to those two documents. I'll give you a second to look at it. So what we're doing here is we have this ranking function that we're learning, F. We're using F to compute the score of D sub I, the relevant document, and we're using F to compute the score of D sub J, the non-relevant document. So F here we can think of as some sort of neural network. The details aren't so important for us. You can think of it as simply a stack of fully connected layers. By that I mean a feed-forward layer, a dense layer, whatever terminology you're familiar with. I would consider these to be the same thing. So this is a neural network that takes that feature vector DI as input. It processes it with one or more, say, feed-forward layers, maybe with non-linearities in between. So you can think of this as a multi-layer perceptron even. And then a score is produced at the end. So we do this for D sub I, we get one score out there. And we do this for D sub J, we get another score out there. The purpose of the model, or the purpose of this loss, is then to compare those two scores, and we want the difference to be as high as possible. So because we know that D sub I is relevant and D sub J is not relevant, we want to push D sub I score up and D sub J score down. And rather than saying, for example, that D sub I should be 1 and D sub J should be 0, we care about the relative distance between them. So the specific scores don't matter so much here as the fact that we have a large margin or some large distance between those two scores for D sub I and D sub J. And there's a parameter gamma to control how this loss works out numerically. I think that's not so important for our purposes. The main thing to take away here is that we're looking at a pair of documents, a pair of document representations, I should say, and we want to increase the distance between them. The reason for that being that we want to increase the distance between the relevant and the non-relevant document. So that previous slide was looking at a pairwise loss where we look at two documents at once. We look at D sub I and we look at D sub J. Now, An issue with that, as I hinted at 2 slides back when we were talking about the different types of losses, is that there can be some pairwise losses, errors that matter more than other. So it depends, of course, on the scenario we're in. In the scenario here, and in many of the examples I'm using, I'm thinking of a general web search scenario because I think this is a common ground for everyone. So in web search, it's well known that people don't look at a huge amount of the ranked list. People, it's unusual to scroll past the first page. Now that mobile phones are, pretty common, it's unusual necessarily to scroll even far down on the first page. So based on this intuition that we're now looking at web search and we don't expect people to, go very deep in the ranked list, well, we can say that swapping documents at, say, positions 1 and 5 is a lot worse than swapping them very far down the list. Because really, they're probably not going to get to positions, say, 50 and 55 at all. So even if we have the non-relevant document above the relevant document at positions 50 and 55, this isn't such a big deal. The user is unlikely to even get there in the first place. However, if we place the non-relevant document at position 1 and the relevant document at position 5, the user is really likely to notice that. If the user is searching for anything, of course they're going to see what's at the top few positions because they're going to look at the results. So the intuition here is that pairwise loss, it considers distance between pairs, but not all pairs are equally important as far as our use case and the sort of model we're trying to create. We can live a little with swapping, positions 50 and 55 if it means we get positions 1 and 5 correct. Just to be totally clear, when I talk about positions 1 and 5, I'm of course talking about the documents at those positions. So a listwise loss is how we kind of handle this situation. I'm showing you a very straightforward listwise loss here as far as these things go. It's called lambda rank. And the basic idea is that we want to weight those pairwise losses by a penalty that indicates how much we care about this particular swap. So we have RankNet at the bottom as before. This is the same pairwise loss as on the last page. And we have this new quantity, delta and metric, which is how much the metric we care about changes when documents are swapped. So if we're using a metric like NDCG, if you're not familiar with NDCG, that's fine. The only thing you need to know about this metric is that it measures the quality of a ranked list or the utility of a ranked list, and it's very heavily weighted towards the top positions. So it reflects the behavior I'm talking about here, where swapping, positions 1 and 5 will hurt the metric much more than swapping positions 50 and 55. So if we have a metric like that, we can weight the pairwise losses by that metric in order to indicate, to make things a little human, to indicate to the model being trained that we care more about that position 1 and 5 than that position 50 and 55. And then the reason we might, need to do this in the first place, rather than saying, get all the positions right, is that we want the loss to be higher. We want a bigger influence on the resulting model when we make mistakes like swap the first 2 positions rather than later ones. Obviously, if everything was perfect and we could get everything right, that would be ideal. But in practice, we want to push the model towards the kind of behaviors that we care about more. So this ends the offline learning to rank section. I'll give you a few minutes or a few seconds to think about whether you have any questions on that section before we move ahead to online learning to rank. Just to characterize the difference with offline learning to rank, we're assuming, or we have assumed, that we know what queries and document pairs have a relevance relationship and which are non-relevant. So given a query, we have some list of relevant documents and we have some list of non-relevant documents. And we're using these in conjunction with one of these loss functions to train some sort of neural model. With online learning to rank, we're going to collect information as a user interacts with the system. So the general idea here is that we have some sort of trade-off. So in the offline setting, um, the setup is somewhat clean in the sense that we collect some queries, we judge some documents for relevance with respect to those queries, and then we train the model, and we can also evaluate the model using judgments. Of course, we don't want to use the same queries and documents that we train the model on, but we can, follow standard machine learning practices and, create a train set and a test set, train on those train queries, test on those test queries, and have some idea of how well our learning to rank model is doing. Online learning to rank instead leverages users interacting with the system to learn a ranking function. So this, of course, has different trade-offs. The first, which is a big advantage, is that assuming you already have some sort of system that users are interacting with, it's very inexpensive to collect these clicks compared to human annotations. We would have to pay an annotator, we'd have to pay an annotator to work for a substantial amount of time to indicate which documents are relevant to each query, whereas users are already using the system and clicking. Another advantage is that this captures actual user preferences. So we don't ask an annotator what the system should do for everyone. Instead, we see how users are interacting with the system and can capture the actual preferences of the users as they click on things, as they interact with the system, essentially. And in some cases, this may even have better privacy properties because there's no human annotator that's going to look at the data. You can imagine maybe in some fully automated way that no human sees, this online learning to rank could be deployed, whereas we wouldn't want to take those documents and show them to a human to say that this is relevant to the query or not. And this is also related to actual user preferences, because even if we're thinking of a situation where maybe there's not a privacy risk, something like general web search where everyone can see Wikipedia, what the user is looking for is subjective. So I might mean something different when I say Apple than someone else means. I might have my own idea in mind, and maybe the system could be personalized to what I'm expecting somewhat. Now, this all sounds great. Really, the only downside we saw is that the setup is more complicated, and of course, we have to start somewhere. We need to start with some sort of initialization of a ranking function. But there is a big difficulty, and that users don't only click on results, if we think about web search, because they're relevant. So there could be many different reasons someone clicks on a result. There could be some, accidental movement of the mouse and click, and actually we're okay with that because we assume these accidental movements are noise. They're random, so they would randomly happen to all of the results displayed. So they will kind of average out in the end. But we do care about types of bias that influence how a user interacts with the system. So thinking again of web search, this common scenario that we're all familiar with, there could be position bias. In fact, there is position bias, at least as I've described web search, because top ranked positions are always more likely to be clicked. If I place a document that is not relevant at position 1, and I place a document that is not relevant at position 50, even though both of these documents are not relevant, even though neither document is really useful for the user in their query, the document at position 1 is going to get clicked more simply because the user is going to see things at position 1 far, far more often than they see things at position 50. And this is also related. Yep.
There is a question, Andrew. I don't know if you can see it in the chat. No, so I can read it for you.
Okay. Yeah, I cannot.
Is this online learning personalized per user, or is there one learning result from all users' interaction?
Yeah, that's a good question. The more straightforward way would be to one result for all users' interaction, but it could also be personalized. So it could be either essentially. So I'm mostly going to talk about it in the general setting. But if there's enough data, if a user interacts with the system for a long amount of time, or if we can group users in some way, then we could personalize it to that group or to that specific user. So there's nothing fundamental about this approach that dictates whether or not it's personalized at the user level, other than the fact that, of course, some interactions need to be collected. And the set of all users, of course, interacts with the system more than a single user. But it really depends on the platform and the use case, the scenario, all of this to say, whether or not it could be personalized to a user level, or maybe whether that user could be assigned to some group, like maybe a group of expert users who look for different things than the users who are new to the platform, and so on. So I was talking about position bias, where top-ranked positions are more likely to be clicked. And this is also related to selection bias, which is simply that, if a user doesn't go down to result 100, they clearly cannot click result 100. And of course, there are other biases here. Before we go on to talk more about online learning to rank, we'll have another WooClap question. So I'll read the question and then I'll give you a few minutes to enter your answers. Online learning to rank is an advanced approach in which a learning to rank model is trained using relevance judgments created by experts. True or false? So we're thinking about about the definition of the phrase online learning to rank and how these models work. I'll give you a minute or two to think about it and enter your answer if you haven't yet. One hint, as far as a useful angle to approach this question from, is to think about the difference between online and offline learning to rank. I'll give you about one more minute to enter your answers if you would like. Okay, I think we can go ahead and take a look. Give you a few seconds if you want to sneak in a last minute answer. So 19% of people say true, that this is an advanced approach trained using relevant judgments created by experts. And the majority, 81%, say false. This is not an approach using relevance judgments created by experts. The correct answer is false. So it is an advanced approach, of course, but the key thing to think about here is that we're training the model using interactions from users. We're not training the model using relevance judgments created by some sort of annotator or outside expert. maybe it would have been better to use the term annotator. Offline learning to rank would be an approach where the learning to rank model is trained using relevance judgments created by experts, whereas online learning to rank is a learning to rank approach using interactions from users interacting with a live system. If anyone has any questions, I'll let you go ahead and ask as I move slowly to the next slide. So as I hinted at, excuse me, the key difficulty with online learning to rank is we need to remove bias from how the users interact with the system. So our goal is, of course, to optimize a ranker that satisfies users' preference using their interactions. But we know user interactions with the system are biased to different extents, and we need some way to debias, to remove that bias. So you see one form of bias here, and this is called the golden triangle. So this is indicating what a user is looking at when they see the search engine results page. So this is produced with eye tracking. So the user is wearing some sort of equipment that records essentially where on the page their eyes look at and for how often. So what you see is the top left corner of that page. A lot of time is spent. And then as we move away from that corner, as we go to the right, as we go down, users spend less and less time looking at the results. And so it follows, if they don't look at results further down, they're also not going to click them. So this is a really clear example of position bias and how users interact with search engines. Now, the general idea of online learning to rank is we need to remove this bias in some way. Counterfactual learning to rank uses propensity weightings in order to debias interactions. So what that means essentially is that you create some sort of propensity estimate of how likely someone is to look at or click on position one, regardless of anything else. And then these propensity estimates can be used to debias interactions that you've observed and logged. So to say this in a bit more of an informal way, we can say something like, well, most of the clicks happened on position one because that item was top ranked. And this already hints at different ways to obtain these estimates. If we put a relevant item at position one and a non-relevant item at position one, we can compare how often they're clicked to get some idea of how often an item is clicked simply by being at position one. So once we've debiased those interactions, we can train a learning to rank model as before, as we would in an offline learning to rank setting. So this is essentially creating some sort of training data that, rather than annotated by experts, is based on user interactions and accounting for biases that affect how those users interact with the system. To go into a little bit more detail, the way we obtain a propensity estimate is, of course, related to the bias we have in mind. There's, unfortunately, no easy way to account for every bias that might exist. We have to understand how someone interacts with the system and what is going to be, biasing their interactions. So I use the standard example of position bias. And here with position bias, what we need to do is separate the relevance of an item from the position it was shown at. So I briefly mentioned on the previous slide, this we can run something like an A/B test or selectively swap two items. So we can say if we swap a relevant and a non-relevant item and compare how often they're clicked at two different positions, we can get some idea of how the position is biasing interactions. Alternatively, we can assume some model of user behavior. We can say something like, well, users continue clicking on links until they find a relevant one, and there's some chance of them moving from the first thing they look at to the second, and so on and so on. And based on a model like this, we could also estimate a propensity and debias interactions. Really, the key point here is we need to have a bias in mind, and then we need some way to compute how that bias is affecting things, a propensity estimate, so that we can then look at the interactions we've logged and modify them in some way. With position bias, we might divide the click count by the probability of looking at something that's at that position, so that we account for the fact that many of these people or many of the users are simply clicking on an item because it was at position one, for example. So this is fairness and learning to rank. But again, please feel free to ask if anyone has any questions, both on the previous material and on the next material as we continue. So now we want to talk about different types of fairness methods, but specifically in the context of learning to rank. As you've seen before, we can break these down into 3 different categories. We can talk about pre-processing, which is modifications to the data before it reaches the ranking model. We can talk about in-processing, which is some modification of the ranking model in order to consider fairness constraints. And we can talk about post-processing, which is some modification of the output of the ranking model in order to ensure some sort of fairness. So again, the way to think about this, pre-processing is what goes into the ranking model, in-processing is what happens inside the ranking model, and post-processing is what happens to the output of the ranking model. To make that a little bit more formal, pre-processing methods seek to mitigate discriminatory bias in training data, and they have the advantage of early intervention on some sort of pre-existing bias. However, there's also the disadvantage, because this is happening on training data going into the model, it doesn't necessarily guarantee anything about the output. So we can't guarantee this way that the output will be unbiased. The idea of in-processing is to learn a bias-free model by both maximizing utility and minimizing fairness. Sorry, by both maximizing utility and fairness. And this creates a good trade-off between utility and fairness, but it's not guaranteed that, of course, the model will create a fair ranking on data outside the training data. So to rephrase that little part a little bit, here we're using a loss that encourages the model to treat the training data fairly with respect to some notion of fairness, which we'll get into later. But the fact that the training data is handled in a fair way does not necessarily mean that other data will also be handled in a fair way. And what we, of course, really care about is that other data, the data that our model is used on in practice, not only the data the model is trained on. So this can create some sort of guarantee for the training data, depending on how everything is set up and how much we weight that fairness objective. But again, it's not guaranteed that what comes out of the model will always be what we want. We might still get an unfair ranking. Finally, the post-processing methods actually re-rank the output of the model. So if we're thinking about ranking humans, maybe in the context of job search, then we can re-rank candidates subject to some given fairness constraints, and we can ensure that those constraints are met, but of course the utility might decrease. We might just not be able to satisfy specific constraints without in some way decreasing the utility of our ranked list. It of course depends who is in the ranked list and exactly what we're ranking and so on. So these different approaches all have different trade-offs. With in-processing, we at least encourage the model to create a fair ranking and to maximize utility. But of course, whether this generalizes is hard to say. It depends on the specifics of the situation, on specifics of the data. We can't say that just because we use an in-processing method, now everything our ranking model produces is fair. Post-processing, on the other hand, we can guarantee that we meet some fairness constraints, but we don't give the model an opportunity to learn how to balance these. We may be hurting the utility because there's no way to consider these jointly. We're only coming in at the end and saying, here's the outcome we want, and hopefully this will be good in terms of utility still. And of course, pre-processing is kind of the opposite of that post-processing. So with pre-processing, we're trying to reduce bias in the data as much as possible. Whether or not we do that will, of course, have a big impact on what comes out of the model, and the model is still attempting to optimize for utility. So we can go to our first WooClap question of this section. It's again a true or false question. So the question is, pre-processing methods modify data to ensure it results in fair outcomes by removing sources of discrimination. True or false? I'll again give you a few minutes to enter your answers and think about the question. give you, say, one more minute. Okay, last chance if you'd like to enter an answer. You have a few more seconds to do it, and then we'll take a look at the results. So about 56% say true, and 44% say false. Again, the question is whether pre-processing methods modify data to ensure it results in fair outcomes by removing sources of discrimination. Again, this is a little bit of a tricky question, but the key term here is ensure it results in fair outcomes. While pre-processing methods attempt to improve the outcomes from that data by removing, the pre-processing removing sources of bias, they aim to remove sources of bias. It's not necessarily the case that this will, necessarily result in a fair outcome. So again, the key phrase here is ensure it results in fair outcomes, which is of course tricky. All of these methods attempt to improve the fairness of outcomes in different ways, but it's only the post-processing methods, the methods that operate on the final output of the model, that are enabled to ensure fairness. I'll go ahead and move to the next slide slowly. Feel free to ask any questions. So let's talk about pre-processing methods in a little bit more detail now. Again, these are methods that operate on the input data to a ranking model. And because they're operating on the input, not on the output, while they can attempt to encourage fair outcomes, there's no way to guarantee this. The first pre-processing method we'll talk about is LFR, for learning fair representations. This is a seminal paper in this field. And this paper targets what they define as group fairness. So this essentially means that people in different groups, that means that groups are treated fairly. So the idea here is to create a mapping function that maps each person to a prototype vector. So the input is a feature vector representing each person or each item that does include sensitive attributes. This is not needed at test time. And then as an output, the model creates a vector that should remove correlations between these sensitive and these non-sensitive attributes, while also ensuring that candidates from different groups are similarly likely to be mapped to the same cluster or prototype vector. So the idea here is to map items to this cluster of items and then treat that cluster in one way or another. So we're losing some specificity for the individual item or person being ranked by mapping to that cluster, and then we're operating on the cluster with the hope that we've removed correlations between these sensitive and these non-sensitive attributes, so that the ranking or the output of the system is based only on the attributes that are relevant to the task, rather than also these sensitive attributes. So the way this looks in practice, we have three components to the loss. We have a data loss. This is L sub x. The idea here is to ensure that the feature representations change as little as possible. So x is the original data. X prime is the data after mapping to these clusters. So every user is a combination. This is a weighted average of the different clusters that exist. So we take those clusters and we put them together with one weight per cluster in order to create a new representation X prime of that user. So this is that mapping to prototype vectors I talked about. The L sub Y is a utility loss. The idea here is to have some supervision on the outcome of the process. So for example, to say, this person or this item should have been ranked highly and they are, or should have not been ranked highly and they are not, or an error was made and so we need to have a higher loss to move things around. And then we have this L sub Z, which is the fairness loss. And this is based on these prototype clusters, or the mapping to the prototype clusters. And this is to ensure that candidates from group A have the same probability as candidates from group B to be mapped to a specific prototype cluster, prototype vector or cluster. So the idea here is that these clusters we create, or these prototype vectors, don't encode sensitive attributes, that regardless of the group a person belongs to, regardless of their sensitive attributes, they're equally likely to be mapped to any of the clusters. So this is trying to avoid a situation where the clusters themselves simply encode some sensitive attribute that we would not want to make a decision based on. Each of these losses has a weight. This is a hyperparameter. They have different ranges. They can be weighted in different ways. But the general idea here is we're combining some reconstruction or data loss in order to ensure that the original features don't change too much. Some utility loss to ensure that the outcome using the new feature vector is what we want, is correct in the sense of we don't lose all utility from the model. And then some fairness loss in order to ensure these sensitive attributes are not considered when creating these clusters. And again, these clusters form the new representation for users. The next method we'll look at is IFIR. This changes a little bit in terms of whether you think of fairness towards groups or towards individuals, but in terms of the method itself, it's fairly similar to LFR. So they define this method as targeting individual fairness. What they mean by that is to treat similar people similarly rather than treat groups similarly. And this mapping function creates a representation for each person again as before. As before, the input is a feature vector that may include sensitive attributes. These will not be used during test time, but we need to have some idea of group membership so that we can ensure that this is not encoded in the representations we create. And this, again, outputs a vector that does not have the correlations, or ideally does not have correlations between sensitive and non-sensitive features, with the constraint that similar candidates in the original feature space should remain close to each other in the new feature space. And this is again accomplished by mapping to these prototype vectors or clusters. So the motivation is a little different, but a lot of the machinery as far as how this is set up is the same. So as I said, machinery is very similar. Again, we have a data loss and a fairness loss. The data loss is again the difference in the original feature vector and the reconstructed feature vector. So based on this, these prototypes. So again, on the right, you see that this X prime, this new feature vector, is a weighted average of different prototype vectors or clusters that the user belongs to. The data loss is the same as with LFR. The fairness loss is a little different. So here, rather than considering groups, the distance between different candidates is considered. The idea is to ensure that similar candidates remain close to each other in the new feature space. So the idea is that if a pair of candidates was close to each other originally with their original feature vectors, they should remain close to each other in the new feature space after correlations between sensitive attributes have been removed. It's worth noting that this notion of close in the original feature space might be problematic depending on the original feature space and how it's defined, because of course we don't want to consider things like sensitive attributes when considering closeness. So these should be removed when computing the distance in that original feature space. But otherwise, this is quite similar to LFR as a preprocessing method. They have slightly different goals, slightly different losses, There's no utility component here, you see. IFAIR relies on the reconstruction or this data loss in order to keep the utility of the resulting representations. And they're targeted at slightly different considerations. IFAIR for treating similar people similarly, LFR targeted towards groups. But the machinery for both is the same, and both are pre-processing methods that take in an input feature vector, somehow rewrite that feature vector, so to speak, to remove correlations between attributes that shouldn't be correlated, and then give you a new feature vector that can be used for your downstream task. To show you an example from a recent study that Clara did, we have features in 3 spaces. On the left is the original feature vectors. This is a TS08 plot, so it's simply a visualization of how close different individuals are. Yellow indicates one group, the blue dots indicate another group. So we see in the original feature space, there's some clear separation between some of the blue dots and most of the yellow. With LFR in the middle, the groups are much closer together. In terms of this visualization, this TS&E visualization, they're much less separable. The feature vectors are more similar than they were before. And then on the right, you see an example with IFAIR, where things are perhaps less similar than more similar than they were before in the original, but the effect is not as strong with LFR. So we see there's still some trends here where the blue dots are close, but not so far away from the yellow dots, which is somewhat similar to the original. This is because we're looking at individual fairness here, and this is trying to preserve the similarities that were in the original feature vectors. Whereas with LFR, where we're considering groups just like we're visualizing, we see that the feature vectors place the points much closer together in this resulting new feature space. So these are 2 examples of pre-processing methods. If anyone has any question, feel free to ask. Next, we're going to move on to in-processing methods. And recall that these are methods where we modify the learning process of the ranking model in order to try to achieve some balance between utility and fairness with the model being trained. So the method here for in-processing that we'll look at is called delter. This is a listwise fairness approach. Recall from about an hour ago that with listwise losses, we're looking at a list of items, or here a list of humans being ranked, a list of individuals. And so we're supervising the model's operation, how it should perform the ranking based on that list. So the training data here is a set of, it's offline training data. So this is a set consisting of queries and then ordered items for each query. Items belong to either a protected group, for example, females, or a non-protected group, for example, males. And we're modifying the loss function used in this offline learning to rank approach to balance both utility and fairness. So we see on the left, we have this utility objective. This considers the labels only. And we have this fairness objective on the right. That's how much we want to optimize for fairness. So rather than simply optimizing this utility loss, which could correspond to a previous listwise loss, where we want, for example, a relevant labeled item to be higher than a non-relevant labeled item, here on the right, we're also including a quantity that considers what exactly those labeled items are. Are they from the protected group or the non-protected group? We want to be fair to both in the sense that both should ideally be ranked highly. And so using this loss with the model, we can try to optimize some fairness objective that we'll talk about on the next slide. Actually, we have a WooClap question first. So before we discuss the specific fairness objective, let's think a little bit about the role of in-processing. So true or false, in-processing methods modify the learning to rank algorithm being used. I'll give you a couple minutes to think about it and answer. So this is about the definition of what it means to do in-processing for fairness, as opposed to pre-processing or post-processing. I'll give you another minute or so to think about it and enter an answer if you'd like. All right, we'll take a look in a second. So go ahead and get your answer in if you'd like to. So everyone, 90% of people say true, 10% say false. And true is the correct answer here, in the sense that they modify the loss function used by the learning to rank algorithm. And as long as we think of the loss function as part of that learning to rank algorithm, they do modify the learning to rank algorithm used. Feel free to ask if you have any questions on this. I think the key point is that the learning to rank algorithm consists of this neural network and also the loss used to train it. And so in this sense, in-processing methods do modify that algorithm. I'll slowly move to this slide and we'll start talking about how this fairness objective is defined. But again, feel free to ask if you have a question. So a key ingredient in this delta was that L sub fair, or that fairness loss component. We saw the utility loss before with listwise metrics and learning to rank in the general offline setting. And what's new here, or one of the things that is new, is this L fair component to encourage fairness. So what this is doing is it's comparing the exposure of two different groups based on the idea that different groups should get the same exposure. Of course, different groups can't get the same exposure for every single query. Only one group can be placed only one person can be placed at the top ranked position, of course. So this is considered over multiple queries. Exposure is essentially defined as how often that item or that someone from that group is placed at position 1. So if we're thinking about many scenarios, we can think about position 1 directly, because this is the position that is most likely to be viewed by the user. So this approach makes that assumption to simplify things a little bit, that all we really need to keep track of is position 1, and we'll look at the top 1 probabilities of predictions in order to see how often something is placed there at position 1. And of course, this is averaged, as I said, over different queries. Now, this is just one fairness loss. It's not that we need to use this one specifically. This one is based on this demographic parity of exposure idea that I mentioned, that groups should get the same exposure. But we could plug in any other differentiable fairness metric, any other type of fairness loss into the model, as long as we can take the derivative of it. And of course, this is needed because we're training these models with stochastic gradient descent. This brings us to different ways of measuring fairness. So what we just saw is demographic parity of exposure. This is the idea that groups should get the same exposure. An alternative way to look at it is that exposure is proportional to utility. So rather than saying that all groups should get the same exposure, this notion of fairness would say that groups should have an exposure proportional to the group's utility. So based on how many items in that group are marked as relevant or is marked as something that should appear near the top, that should influence how often that group itself appears near the top. I suppose this is philosophical. I suppose this is also very dependent on the use case and the scenario. There must be examples where the utility should be considered. And of course, there are other examples where we can assume that every group should get the same exposure because there are relevant items, so to speak, from every group. This brings us to the final family of methods, the post-processing methods. Again, feel free to ask if you have any questions on the previous slides in processing and pre-processing. We've looked at a few examples so far, just to recap before we move into post-processing. We've looked at delta for in-processing, which takes that initial offline learning to rank we looked at and modifies it to include a fairness component in the loss. So we're looking at a list-wise loss based on utility, but also a list-wise loss based on fairness to consider the idea that across different queries, members of each group should appear at the top one as the top ranked candidate. And then before that, we also looked at LFR and IFAIR. LFR stands for learning from fairness. And these methods were a little different in terms of what they tried to achieve, similar users being ranked similarly, or fairness between groups, but both took a somewhat similar approach where they mapped feature vectors or candidates to these prototype vectors, or a weighted average of prototype vectors, which did not contain information about sensitive attributes, at least ideally. We're now going to talk about post-processing methods. These are the methods that can actually ensure some fairness constraint is satisfied. And the reason they can actually ensure that is because they intervene on the outcome. So in other words, they modify the output or the ranked list directly. So FAIR, top K rankings with multiple protected groups, FA star IR, is one approach for doing this. The idea here is a ranking is considered to be fair if for each top K, the proportion of protected group members does not fall below some minimum target proportion. So this is saying something like, we want 20% of a protected group in the top 5, and we want 20% of that protected group in the top 10 as well. And we consider the ranking to be fair as long as there is 20% in both of these segments. Now, if this proportion is too high, it can mean that we create some different type of maybe undesirable behavior where protected candidates could be pushed up more than we would expect. Although, of course, this is based on the specific scenario and the value of P and so on. The basic idea is to ensure that the proportion of protected group members in these subsets of the ranked list doesn't fall below some desired proportion P. So to do that, we can essentially create separate rankings for each of the groups, and then we can merge them together. To say that more formally, in step 1, We can pre-compute some table that contains the minimum number of protected candidates from each group at each position in the ranking. And this is related to a minimum proportion P. And then we can rank the groups separately by decreasing scores and merge them into a single ranking according to this table. So there's an example of that here. So let's say we have this model on the left. We have two groups, call them yellow and pink. On the left, all of the members of the yellow group, which corresponds to males in this example, are ranked above all of the candidates from the other group. So we can create two separate lists for each of these groups rather than using that original ranking. So now we have the list or the ranked list of items from group 1, from most relevant to least relevant according to the model's prediction. And we have a ranked list of items from group 2, from most relevant to least relevant based on the item's prediction. And given those two ranked lists, we can now merge them together into one final list that satisfies that property. So you see here, 50% are from each group in the top 4. So this would satisfy a constraint of a 50% chosen value for P. So you see that because this is post-processing, this is operating directly on the output of the model, we can ensure whatever sort of fairness constraint we want, assuming we have items to put in places. This is unlike the in-processing method and unlike the pre-processing methods, and that we guarantee this constraint is satisfied because we're simply modifying the ranked list in such a way that it does satisfy the constraint. So we now have our next WooClap question. The question is, if it is possible to satisfy some given fairness constraints, post-processing methods can ensure that they are always satisfied. True or false as before. So again, I'll give you a few minutes to think about it and enter your answers, and then I'll see if there are any questions or anything we want to discuss about the question. I'll give you 30 seconds or so if anyone wants to get a final answer in. A few more seconds. Last chance. Okay, let's take a look. So again, the question, if it is possible to satisfy some given fairness constraints, post-processing methods can ensure that they're always satisfied. There's a little bit more of a split than last time, but clearly favoring true. So 61% say true, 39% say false. The correct answer is true. A key part of this question is if it is possible to satisfy some given fairness constraints. Of course, we could imagine situations in which this constraint simply can't be satisfied. Maybe we've come up with a constraint that simply cannot be satisfied. And so in this case, yes, no post-processing method could satisfy the constraint. But given this case where it is possible to get the behavior we want, so for example, 50% of people from each of the two groups in the top 10 of the ranking, a post-processing method can ensure that we always get this behavior because the post-processing method happens at the very end of the pipeline. A key point to recall is the post-processing method is operating on the output of that ranking method or on the ranked list that's created. And this is the very last thing in the pipeline. So the post-processing method can move the results around however it wants in order to ensure that its fairness constraint is satisfied. So this is true. If anyone has a question, feel free to ask. I'll move slowly to the next slide. So I want to very briefly talk about one other type of post-processing method called equity of attention. The idea here is that documents at different positions will receive different attention. This goes back to that notion of position bias. A document or a person ranked very low in the list is not going to receive much attention, whereas one at the very near the top is going to receive queries and views by different recruiters or different people interacting with the system and so on. And so the idea of equity of attention is that we should amortize this, and unfairness is the difference between the document's exposure and its utility. So the idea is that something is unfair if a document does not receive, or an item or a user does not receive much attention, but it should have. We won't go into the details of this method very much because it's takes some discussion, but essentially there's some fairness constraints, and this is optimized as an integer linear program. We'll move on to the last part of this lecture today on fairness in online learning to rank. We've been discussing methods that can be used in an offline setting, and now we're going to briefly discuss one that can be used online. So recall that when moving to an online setting, we're using interactions to optimize relevance. Now we're adding in the constraint that we should also be respecting fairness, or ensuring that we learn a fair model while also optimizing relevance. So as before, as in the online learning to rank section topic, not considering fairness, interactions need to be debiased. We also, are worried about things like position bias. We don't want a rich get richer effect where because someone or something is always ranked at the top position, it continues to be ranked at the top position. So we can add in some sort of fairness constraint to the online learning to rank process that considers exposure, similarly to how Delta does this in an offline setting. So we can imagine adjusting things by considering examination probability. So this is again a component of the loss, similarly like we saw with Delta, to consider group membership when considering where things should be ranked. So we have this quantity of groups exposure on the left. This is analogous to how Delta looked at the top one, how often members of a group appeared in the top one. And so this is computing the average examination probability for every group. This is the group's exposure. And on the right, we have what they call the group's merit. This is just the utility. So this is the average utility of that group. And so we want to balance these two quantities, the utility of the members of a group and how often they're shown to the user. So we would modify the loss similarly to Delta in order to include this group's exposure component. And this is done over time. So we have this disparity between two different groups. And so this is comparing how often the user is observed, how often the item is ranked to the merit for two different groups. And then the disparity is the difference in this proportion. So if two different groups have equal ratios of exposure to merit, there will be no disparity based on this. And so this disparity is the specific formula that is plugged into the loss in order to optimize this fairness constraint, or this fairness objective. It's not really implemented as a constraint here. So this brings us to the next WooClap question. A fairness-aware online learning to rank method that considers a group's exposure and utility would be categorized as an in-processing method. So we talked about pre-processing, in-processing, and post-processing in the context of fairness-aware offline learning to rank. And now we want to think about how this changes in an online setting. So with this method we just looked at, it considers a group's exposure and utility be categorized as an in-processing method. True or false? As before, I'll give you about a minute or two to answer. Then we'll have a quick opportunity to discuss the question and wrap up the lecture shortly. Looks like we have quite a few answers in. I'll give it 30 seconds or so. So feel free to enter your answer if you would like to. Take a look in a few seconds. Last chance if you'd like to enter an answer. Okay, so most people say true, about 76%, and 24% say false. True is the correct answer. So you can think of this analogously to delta, where what we've done is we've modified that objective function for the model, or the loss function, that modifies the model's algorithm. And so this would be an in-processing method. We've modified the model itself rather than modifying the model's input, as we would do with pre-processing, or modifying the model's output, as we would do with post-processing.